All right, here's problem 11 off the math subject GRE practice exam. What we're doing here, these are solids of revolution, I think is what they're called. The region bounded by the curves y equals x. So that's this diagonal line, as I'm sure you know, and y equals x squared, that's our parabola. There's a poorly drawn parabola. Those guys intersect at the origin, 0, 0, and up at this point at 1, 1. And what I'm going to do is I'm going to take this region in the first quadrant. I don't know why they specified that, because it's the only place these guys are bounded, right? Yeah, otherwise it'd be infinite area. Anyways, I'm going to take this region and I'm going to rotate it around the y-axis here, and that will create a three-dimensional solid, and what I'm asked to do is find the volume of that solid. Two different ways to do this. I'm going to do it both ways. The way I think I prefer would be the washer method. And the way to think about the washer method is if you take any horizontal slice of this thing, what you would see would be something that would resemble a washer. It would be a circle with a circular hole missing from the inside. And so all I got to do is kind of add up the area of each of those washers. And there's infinitely many, so I'm kind of using these terms loosely. And that'll give me the volume of the resulting solid. So the way you add up infinitely many things is to use your integrals. So since I'm cutting this thing horizontally, really what's changing each time is my y-coordinate. I'm going to integrate from 0 to 1, and y will be my variable of integration. And then what I got to do is just think about what any given slice would look like. Well, it would be a circle, as I said, and the radius of that circle would be this distance right here. But then it would also be missing a circle, and the radius of the missing part would be the distance from here to here. So how do I represent those distances? Well, the distance from here all the way over to here comes from this curve y equals x squared, but y equals x squared really describes the height of this. The x squared is the height, or y is the height, and as a function of x, it's x squared. So what I want to do is describe this distance, not this distance. So the way I do that is I solve this guy for x. I get x equals the square root of y. And now what I can do is say, okay, my washer, it would start with the circle. The formula for the area of a circle is pi r squared. R in this case is the square root of y. But it's not just a circle, it's a washer. It's missing the circle on the inside. The circle on the inside has a radius of the distance from here to here, and that comes from my curve y equals x. And so if I solve y equals x for x, well, it's kind of already done. You get this y here. So I get pi times y squared. If I figure out this integral, it would be my answer. So maybe you pull out the pi first. A lot of times when you see this formula in a book, the pi will already be pulled out in front because that happens every time. But I figured I'd do it in the next step because then it's more intuitive where this stuff comes from. The square root of y squared is just y. So this is the integral I'm trying to take. It's an easy enough integral. I got 1/2 y. Whoa. Let's try that again. It's the antiderivative of y would be 1/2 y squared, or y squared over 2, however you want to write that. And the antiderivative of y cubed, or of y squared, it's hard to write one thing and say something else, for me anyways. That would be y cubed over 3. And I want to evaluate this thing from 0 to 1. So that's just pi times the difference between 1/2 and 1/3, which is a 1/6, because this is 3/6 and this is 2/6. So I get pi over 6 as my answer. So B is the answer to this question. As I mentioned earlier, there's another way you can do this. You can think about this as cylindrical shells. I think this is less intuitive. Most people don't like this way. The advantage here is that x will be my variable of integration. Because what I'm doing now is, instead of thinking about this as horizontal slices, I'm thinking more as a vertical slice, but not really. Because remember, this is this three-dimensional thing. So what I'm doing is I'm kind of picturing that if I could, what a student of mine said is, think about this as like a Russian nesting doll. So I'm doing a poor job of drawing this, but if I took any slice here and kind of thought about the resulting cylinder that that guy would create, it would look something like this. And so if I could figure out the surface area of that cylinder, then I could add up infinitely many of these cylinders, kind of Russian nesting dolls all inside each other. And then that would make up the volume of this entire solid of revolution. So the way I figure that out is I'm taking an integral, and my integral is going to go from 0 to 1, but now that's the x coordinate going from 0 to 1. So dx will be my variable, or x will be my variable of integration. And the reason that it's dx is because if you think about the surface area of a cylinder, so if I cut this thing right here and unfolded it, I just have a big rectangle. And that big rectangle, to figure out the area of a rectangle, it's just length times width. Or in this case, the height here times the circumference of this circle all the way around, because I unfolded this thing. So the circumference of a circle is 2 pi r, but the radius in this case is just my x coordinate. So I'm going to put 2 pi x right here. And that x is what's going to be changing. I'm adding up infinitely many of these. In each case, I get smaller and smaller cylinders nested inside each other. So x is my variable of integration. 2 pi x times the height. What's the height of your cylinder? Well, it kind of depends which x you choose. The one I depicted right here, it's this height. But if you did a smaller one down here, it'd be this height. In any instance, it's this top curve minus this bottom curve. So the height of this top curve is just x. The height of this bottom curve is x squared. So if I could evaluate this integral, I'd get my answer. And I can evaluate that integral. Maybe I'll pull the 2 pi out in front, and then I'll take x and distribute it through. So 2 pi times the integral from 0 to 1 of x squared minus x cubed dx. And that's 2 pi times, let's see, that's x cubed over 3 minus x to the 4th over 4. Evaluated from 0 to 1. So that's 2 pi times the difference between a third and a fourth. So that's 1/12, because this is 4/12 and this is 3/12. So 2 pi times 1/12 is equal to, well, let's write that all out. 2 pi over 12, aka pi over 6. Hey, look at that. Same answer either way. So the answer is still pi over 6.